So, we are looking at 1D flows with heat addition, which is a Rayleigh flow. The previous class we looked at the Rayleigh line or Rayleigh curves. So, in a PV diagram it is a straight line, while in a TS diagram it has a curve, and it is very good to know the nature of this curve. So, it has two branches and two critical points. So, this point is where temperature is maximum, and this is a point where entropy is maximum. Okay, so, this corresponds to a Rayleigh curve, and this is for static conditions. You can also draw the corresponding stagnation conditions, and at the point of maximum entropy you have maximum heat addition also. These are stagnation lines, T0 lines, T0 reaches a maximum. So, the maximum amount of heat that can be added corresponds to the location of S maximum, that is the entropy maximum, and this corresponds to Mach number equal to 1. So, all these upper branch cases are of subsonic conditions, while lower branch corresponds to supersonic conditions. So, when heat is getting added in a subsonic flow, the velocity increases, Mach number increases, it drives it towards sonic conditions. This is the subsonic branch for the stagnation conditions, and supersonic branch for the stagnation conditions. Now, in the subsonic flow you also have the maximum enthalpy point or maximum temperature point. So, the temperature initially increases until T max, and thereafter it decreases to S max, that is to the max critical point. While in supersonic flow the temperature keeps increasing, pressure keeps increasing, velocity and Mach number decrease in the supersonic flow. So, being able to draw these curves effectively will be a nice way to look at problems in Rayleigh flow, and then also understand them properly. So, now we go to the equations and see how we can get various quantities for a flow. So, if there is a one dimensional flow and the heat is getting added to this at a certain rate, and flow is occurring. So, it is having M1 at this point, M2 after a certain point. So, pressure, temperature similar. So, just as we did for other flows, for Fanno flow we are looking at ratios P2 by P1, T2 by T1 and so on. In this case we directly go and look at the momentum equation. It is an inviscid flow. So, P2 by, so P plus rho v square is equal to a constant. Now, if you take out P as common, this will be 1 plus rho by P v square, which is 1 plus multiply and divide by gamma 1 plus gamma m square. So, P multiplied by 1 plus gamma m square is a constant. From this you can easily get what is P2 by P1. P2 by P1 is 1 plus gamma m1 square by 1 plus gamma m2 square. Okay, so, we get P2 by P1. Now, we are looking, once P2 by P1 is got, we can look at T2 by T1, and for T2 by T1 we use the continuity equation and equation of state together. Okay, so, because rho 1 V1 is equal to rho 2 V2, and we also use P is equal to rho RT, combine them together. So, that the continuity equation can be expressed in terms of pressure and temperature. Rho is P by T. So, P1 V1 by T1 is equal to P2 by T2, where V is the velocity. So, from here we can get T2 by T1. as P2 by P1 P2 by P1 multiplied by V2 by or divided by P2 by P1 multiplied by V2 by V1, and V2 by V1 is V is Mach number multiplied by acoustic speed, and acoustic speed goes as square root of T. So, we use all these here. So, M2 multiplied by A2, M1 multiplied by A1, and they are getting T2. So, A2 goes as square root of T2. So, finally, T2 by T1 can be expressed because you have a square root here that will come over here. So, it is P2 by P1 whole square multiplied by M2 by M1 whole square, and P2 by P1 we have an expression. So, we get the expression for T2 by T1. So, once we know both P2 by P1 and T2 by T1, rho 2 by rho 1 can be easily got by equation of state. So, you can get rho 2 by rho 1, which is 1 plus gamma M2 square by 1 plus gamma M1 square multiplied by M2 by M1 whole square. Now, what about stagnation quantities P02 and P02 by P01 and T02 by T01, that you can couple it along with the P2 by P1 we have just got, and P02 by P2 by P01 by P1. Okay. So, this is what we need to get. So, this you will get P02 by P01 multiplied by, so this is 1 plus gamma minus 1 M2 square, this is 1 plus gamma minus 1 M1 square, and that should be multiplied by P2 by P1. So, if you multiply this, this will gives P1 by P2, multiply this by P2 by P1, and you will get P02 by P01. So, that is how we get. So, couple both of them together, and P02 by P01 can be got here. Next, we look at T02 by T01. It is the same principle. Now, you have T02 by T2 divided by T01 by T1. This is T02 by T01 multiplied by T1 by T2. If you multiply T02 by T01 multiplied by T1 by T2, and if you multiply this by T2 by T1, you get T02 by T01. Same principle as what was done for P02 by P01. So, and T0 by T is known, 1 plus gamma minus 1 by 2 M square. So, we can now write the expression for T02 by T01. So, using these set of equations, we get P2 by P1, T2 by T1, rho 2 by rho 1, and P02 by P01, T02 by T01. So, but the main principle here when we look at Rayleigh flows is that the heat added Q is Cp multiplied by T02 minus T01. Okay. So, it is Cp T02 minus T01 is equal to Q. So, when we solve some problems, this connection will become clear, but now if you look at these equations, it must be clear. Suppose all the initial values are given, you know M1, P1, T1, and you know the amount of heat added Q, then T02 can be found out, then T02 by T01 can be evaluated, M1 is known. So, we need to find M2, but we get a equation which is not easily solvable, is analytically difficult to solve this in directly. So, the way ahead is similar to what was done in Fanno flows. You look for a reference condition, and for a Rayleigh flow there exists such a reference condition, in the maximum entropy point S max, which corresponds to Mach number equal to 1. So, for Rayleigh flow it is possible to take the reference as the condition where the flow goes to sonic, okay, sonic values. But what we should really underline, very much underline, is that the sonic values that is referred to in Rayleigh flow is fundamentally different from adiabatic sonic conditions. So, this what was earlier referred to. If you had taken T0 by T star for an isentropic flow or an adiabatic flow, they would remain the constant because flow is adiabatic, there is no heat being added. But if you look at the Rayleigh flow, this T star is not a constant, it keeps varying, it is different at different conditions. So, it is different from the adiabatic case. But what you should understand here is that for a given Rayleigh curve or for a given Rayleigh flow, which implies that G is a constant, which is true, it is a 1D flow, steady 1D flow, the mass flux will be constant, and P plus rho v square equal to constant. So, these are the two conditions which goes in evaluating this Rayleigh curve. So, for a given Rayleigh curve, this point is a unique point. So, that should be understood. So, if a flow process in a duct falls in a Rayleigh curve, then it will have a unique star point or a sonic point. So, how do we evaluate it? Take the Rayleigh flow equations that you already have found out, which is P by P2 by P1, T2 by T1, rho 2 by rho 1, and in that you substitute P2 is equal to P, T2 equal to T, and P1 equal to P star, and T1 equal to T star. Then we get P by P star and M1 equal to 1. So, you get 1 plus gamma by 1 plus gamma m square, similarly T by T star, similarly rho by rho star. So, if you want to express P2 by P1, this can be represented as P2 by P star divided by P1 by P star, where the P star is the same for a Rayleigh curve. Similarly, T2 by T1 is T2 by T star divided by T1 by T star. So, once this T star this evaluation is done, then we can represent any ratios in terms of the sonic conditions. And the advantage here, again we are able to we plot all these values in terms of tables, or they are available through calculators. So, that is the ease of using these reference condition. So, if so always the flow drives the thing towards in Rayleigh flow it drives it towards a sonic condition. So, always heat addition achieves sonic conditions. Okay, so how do we go about solving this problem? Suppose we know the conditions, initial conditions, pressure P1, T1 and M1 are known, then and heat added is known, Q is known. So, the basic equation is Q is Cp T02 minus T01. Then if we know the pressure, temperature and Mach number, we can find the stagnation properties T0 using the expression T0 by T1 or P0 by P1. Similarly, you can find stagnation conditions at initial. So, P01 and T01 can be found. Then T02 can be found by using this particular equation relating heat added to the change in total enthalpy. then T02 by T01 can be expressed, and this can be is equal to T02 by T0 star by T01 by T0 star, and once we are able to find T02 by T0 star, we can use tables or calculators to find value of M2. So, once M2 is known, all other quantities can be determined. So, that is how the algorithm or the recipe to solve these problems. Now, we go to the discussions where we look at this is a 1D flow similar to Fanno flow. In Fanno flow, we looked at if the inlet flow is supersonic, then is there a possibility that shocks can occur in the context of Fanno flow. Similarly, we look at the point whether shocks can occur in a Rayleigh flow, and the analysis is also very similar. Shock equations are rho 1 V 1 is equal to rho 2 V 2 and P 1 plus rho 1 V 1 square equal to P 2 plus rho 2 V 2 square, and so this is G, and this is a constant. This is true for Rayleigh flow also, and of course H naught is constant for a shock. So that is H plus V square by 2 is a constant. But can this be located on a Rayleigh curve? Yes, it solves the first two, it satisfies the first two equations, which are the ones which actually plot the Rayleigh curve. So it will satisfy the Rayleigh curve. Now what one has to do if we have to look at locating a shock on a Rayleigh curve is to look at not just the static conditions but also the stagnation curves. Here you can see the stagnation curves. There is a lower branch and an upper branch. The scale makes it look almost similar, but they are slightly apart, and what we look at is draw a constant H curve, because that is what satisfies a shock, constant H. So, one constant H curve is drawn. It cuts the lower and upper branches at particular points on the stagnation lines. So, they have the same stagnation temperatures, stagnation enthalpy, and look at the corresponding points on the Rayleigh curve. So, they will correspond to the shock points on a Rayleigh curve. So, this is point before the shock, that is 1, and this is point after the shock. So, if you correspond to this one, this is point 2 and this is point 3. Okay. So, that is the point. So, you can locate a shock in a Rayleigh curve. This also brings about an interesting point. In Fanno curve, we have seen that in case a shock appeared in a Fanno curve, then it had an effect on the maximum length of the duct that can be had for achieving sonic conditions, and that was achieved. So, there in the Rayleigh curve, what you were in the Fanno curve, the appearance of a shock actually increased the maximum length. So, if you sort of look at that and remember it, so it will be okay, that is wrong. So, T s for a Fanno is like this, and if a shock appears, then the maximum length, it included a supersonic length and a subsonic length, and that was total length could be higher. But what about in the case of a Rayleigh curve? Will it change the maximum heat that can be added, which corresponds to this particular point? So, if you take any point from a supersonic solution, say point 1, and this corresponds to point 4, and this is the maximum heat that can be added. If a shock appears anywhere in between, Okay, will it change the maximum heat that can be added, and that undergoes no change because a shock does not affect the enthalpy. So, enthalpy is constant across a shock. So, you take at any location, it just changes the flow from supersonic condition to subsonic. So, it moves like this. So, it goes up and goes over like that, but it does not change the total heat that is getting added. So, now if you look at the point that if you consider both a Fanno curve and a Rayleigh curve, Fanno curve also has shocks associated with it, and Rayleigh curve also has a shock associated with it. Is there any correlation between these two? Is there any connection? If you look at Fanno curve, what it considers is rho 1 V1, rho 2 V2, and adiabatic flow H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. This is Fanno, while Rayleigh considers rho 1 V1 equal to rho 2 V2 and P1 plus rho 1 V1 square equal to P2 plus rho 2 V2 square. Now, if you take them together, both satisfy rho 1 V1 is equal to rho 2 V2, and also it satisfies enthalpy remaining, total enthalpy remaining constant, and momentum also remaining constant. P1 plus rho 1 V1 square is equal to P2 plus rho 2 V2 square. So, if you take all of them together, it satisfies all the conditions of the shock. So, an intersection of a Fanno curve with a Rayleigh curve is nothing but the shock. So, you can locate a shock at intersections of Fanno curve and a Rayleigh curve, and for a Fanno curve the stagnation temperature remains a constant. So, the stagnation temperature reference for both the Fanno and the shock are the same, while in the Rayleigh it actually cuts across the two branches. So, if you consider Fanno curve, Rayleigh curve and the shock, all of them can appear as intersections of each other. Okay. So, now we come to another important point, which is that there is a location of maximum temperature or maximum heat added, which is maximum heat added can be located along the stagnation curves. So, it will correspond to this particular point of maximum entropy. Okay, it corresponds to that. So, we are considering, so let us take a subsonic flow. In the subsonic flow, that is the point here 2 0, that is the stagnation point, and heat is being added. So, as heat gets added, it is driven towards sonic conditions, and if it continues to be added and reaches the maximum heat addition point, which is T naught maximum, then you cannot add any more heat beyond this point. So, that is known as thermal choking. So, we have discussed mass flow rate choking in the context of variable area ducts, and friction choking, which relates to the length of the pipe, that in frictional flows or Fanno flows. Now, we come to in the case of thermal or Rayleigh flows, you have thermal choking, where flow achieves Mach number 1 due to heat being added, and that is the maximum amount of heat that can be added. Suppose you want to add more in the case of a subsonic flow, then exactly similar to what happens in a Fanno flow condition, you can have two cases. One is that if you want the flow to remain on the same Rayleigh curve, then the point 2 should be shifted to some other location to double prime, where now there is scope available for adding more heat, but this implies greater pressures. So, more pumping and so on. The other solution that can occur is simply the flow just shifts to another Rayleigh line, where G is smaller, G decreases, that means mass flow decreases. So, this is a 2 prime here where mass flow rate has decreased, but now it can allow larger heat to be added. So, basically when choking happens, if you try to change anything at a choking point, it always affects the upstream. Now, what happens if it happens in a supersonic case? Then in the supersonic case, can a shock change the location of the maximum heat transfer? It cannot change, because shock is a constant total enthalpy process or constant stagnation enthalpy process. So, that would not change, location of a shock would not change the maximum heat being added. It still has to change upstream conditions in order to change the total amount of heat that is being added. But the appearance of a shock allows upstream propagation of information. So, that can change things. So, once a subsonic flow appears, then it can change things regarding pressures and how they are felt upstream. Okay. So, that can happen. And so, now again we can look at influence coefficients. Here the driver is change in stagnation temperature dT naught, which is related to function of the amount of heat added. Okay. So, dT naught by T naught is the driver here. Based on this, we can look at what happens to dm by m, dp by p, d rho by rho, and the procedure for getting these influence coefficients is the same. You write down all the equations corresponding to the conservation of equations, as well as the ideal gas law, P is equal to rho r T. What is Mach number? Mach number is V multiplied by A, and so on. And then club all of them together, take them simultaneously in a matrix form, and from there you can express every other function in with respect to only T naught by T naught as the driving potential or driver. So, if you look at that, then how do these properties change? We have already gone through them. If heat is getting added in a subsonic flow, Mach number increases; in a supersonic flow, Mach number decreases. Pressure decreases in a subsonic flow. Temperature will increase as long as Mach number is less than 1 by square root of gamma. So, it is less than 1 by square root of gamma, but then after 1 by square root of gamma, for Mach numbers greater than 1 by square root of gamma, temperature will decrease. But in the case of a supersonic flow, the temperature will always increase. So, it will continuously increase. Pressures will increase, and velocity decreases in a supersonic flow, but increases in a subsonic flow. So, and always entropy increases in this when we consider heat addition, and nothing stops us from removing heat. If you remove heat, then all the processes get reversed. So, with that we come to an end of the discussions on Rayleigh flow. So, we will do a couple of numericals in order to get really clear understanding of them and apply these principles, and that with that we come towards the end of discussions of one dimensional flows. So, next class we will look at a couple of numericals.